Having seen a join algorithm that takes advantage of our external sorting, you can imagine we probably will come up with a join algorithm that takes advantage of our external hashing. But before we get there, let's do a hash join algorithm that doesn't use external hashing. It's all in memory. And obviously this won't scale nicely, and we wouldn't want to do it in a scalable database system. But it'll give us a flavor of how things work and get us started. Again, this is only going to work for equality predicates, so equijoins or natural joins. And let's assume, without loss of generality, that R is the smaller relation. And with loss of generality, we'll assume that R fits in memory. So we'll obviously extend this later to avoid that assumption. But for now, assume R fits in memory. Then we have this naive simple hash join algorithm, which works as follows. Load all of R into an in-memory hash table, and then scan the file S, and for each tuple of S, probe R for matches. When you find a match, send it to the output. Very simple. What are the memory requirements on this thing? Well, R has to fit in memory, leaving us two buffers, one for inputting things from S and one for outputting output tuples. Okay, so R's got to be less than B minus 2, and there's some overhead for the hash table. So let's call it B minus 2 times the hash fill factor. Okay, so R has to be smaller than that, and S can be any size it wants to be, because we're just going to stream S through. So S can be really, really big, but R has to fit in memory like that. Now, to see how we might extend this to an out-of-core algorithm, here's an algebraic property that might give us some intuition. Look at this query at the top. It's a join of R and S on SID with a selection on SID equals 4 or SID equals 6. And we can decompose that into two separate queries, one on SID equals 4, another on SID equals 6. And we just union the results together because, after all, the stuff on SID 4 has nothing to do with the stuff on SID 6. It doesn't join up, right? The SID 4 on the left and the SID 6 on the right, the joins themselves won't produce tuples that are interrelated. Okay, and we can do this actually not just for SID 4 and SID 6, but really for all the SIDs if we want. So we could take a full join of R and S, and we could break it up into distinct batches of SIDs, where each batch has all the tuples for some particular value of the SIDs, and then the next batch has different SID values, and they just union up at the end together. So think about it this way. We're going to decompose a join of R and S into the union of some selection on a hash value of SID. Okay? And we'll do this for all possible hash values that we can find on SID. And the trick is simply to pick a hash function so that each hash bucket, each batch of values, fits in memory. Let's see how this works. The algorithm that was invented was part of a project in Japan called the Grace database machine. And so it's called Grace hash join in honor of that project, influential project in the early days of database systems. Again, it only works on equality predicates, equijoins and natural joins. It has two stages. In the first stage, we're going to partition tuples from R and S, both of them, by join key and store those partitions on scratch disk. All the tuples for a given key will be in the same partition. So all the tuples for key I from relation R will be in one partition. All the tuples for key I from relation S will be in a matching partition. And then what we're going to do is we're going to build and probe a hash table for each partition as in naive hash join, assuming that a partition of the smaller relation always fits in memory. And if it doesn't, we can do recursive partitioning, as you've seen in unary plain old external hashing. So you remember external hashing, I'm sure. It was a picture something like this. It had a divide phase in which we partitioned and a conquer phase in which we built a hash table for each partition. So we're going to do exactly this for Grace hash join, with the addition that we're going to have a probing relation that's going to work on those hash tables as we go. The probing relation is also going to be partitioned via the same hash function HP, and then we're going to take each partition, 1, 2, up to B minus 1, from the building relation, and we'll build a hash table with it. And then we'll take the matching partition from the probing relation and do naive hash join. We'll scan that partition, looking for matches in memory and sending them to the output. Note again that the probing partitions, just like in naive hash join, can be really, really big. And so all we really care about is whether R can be done without recursive partitioning, the building relation. So here's the pseudocode for Grace hash. And let's see if you can read through this with me. We'll also go through an example with an animation shortly. So for each of the relations R and S, the current relation will be called cur. For each page in cur, we're going to read that page into an input buffer. And for each tuple on that page, we'll place that tuple in an output buffer hash sub p of the join key. If the output buffer is full, we flush it to the disk partition, and at the end of that, we flush all the remaining output buffers. So that's just the partitioning phase of hashing for R and for S. In the second phase then, for each of the partitions we generated in the first phase, for I and 0 to b minus 1, for each page of R sub I, where R is the building relation, for each tuple on that page, we insert it, or sometimes we say we build it into that main memory hash table on hash sub R tuple.join key. So we do that for all of R, and now that Ri partition is in that main memory hash table. Then for each page in the matching S sub I, we read that page into the input buffer on the lower left of our memory box there. And for every tuple on that page, we probe the main memory hash table looking for matches, and we send all the matches to the output buffer. And of course, if the output buffer fills, we flush it to disk. It's that simple.